Good morning, everybody. Thanks to everyone for attending this talk. It's for me a pleasure to introduce you Santi Cassisi, but I guess most of you know him. For those that do not yet have this pleasure, we'll say that Santi Cassisi is one of the most relevant scientists in the theoretical stellar evolution in the theoretical stellar evolution models. He developed the Basti stellar evolution library, which is one of the most used stellar evolution library right now in the world. He published around 350 papers, and he wrote 2 monographs for students and research, which I strongly recommend here. So he is also a specialist in application of the in stellar population, multiple stellar population in a globular cluster and other stellar systems. He is currently a staff member of the Teramo Observatorio, and he is visiting us for the developing of the new extension of the stellar evolution library Basti. So we guess that in the next year we can have this new extension of the stellar evolution library Basti, so we can apply to multi-populations, for example, in globular cluster and dwarf galaxies. He is also one of my best friends, so it's a pleasure for me to here, and he will be here working until the end of the next week. So you can talk with him if you want to talk with him. He's currently in the Antonio's office, Antonio Aparicio office, right here. And today he's going to talk about the signature multiple stellar population in Galactic Globular Clusters. So, Santi, when you want.
Good morning to everybody, and thanks for coming. As you can see, this morning I would like to talk with you about horizontal branch stars, emphasizing some interesting connection with one of the most hot topics that we have currently in stellar astrophysics, that is the presence of multiple stellar population in galactic globular cluster. But also I would like to emphasize some important observational evidence that have been collected in recent time, some apparent anomalies, and also the current shortcomings that we have in a theoretical stellar model for horizontal branch star. Let me briefly introduce for the student the reason for which we need to take care of horizontal branch stars. Indeed, this is the typical color magnitude diagram for a galactic globular cluster, and the horizontal branch is this evolutionary sequence that you can observe here. This sequence is very important because the brightness, the luminosity of this feature is one of the most important primary standard candle distance indicator for resolved stellar population, and also the brightness is tightly related with star counts. In particular, there is a famous parameter, the R parameter, introduced more than 30 years ago by Iben, that is the ratio between horizontal branch stars and red giant branch stars brighter than the horizontal branch. That is one of the most used helium indicator in all the stellar population. And also the subluminosity, the brightness of this feature, the zero-edge horizontal branch luminosity, is determined essentially by the size of the helium core mass at the helium ignition. And since and I'll come back to this point later, the physics entering in the computation of this parameter, the mass of size of the helium core, is strongly dependent on many physical inputs. So this is a very important benchmark for physics, for stellar physics. Another important feature is the color distribution, how the stars are distributed as a function of the color. And this is very important for a well-known and long-standing problem, the second parameter problem. I will not discuss now because I come back on this point later. This is a very famous problem in the context of the Milky Way. And the color location, the distribution of stars along the horizontal branch, depends mainly on the mass size of the stellar envelope. And for this reason, the distribution of horizontal branch star in color has been considered observed a very useful, let me say, observational evidence useful for constraining the efficiency of mass loss along the red giant branch. This, now we know that is not completely correct, and I'll come back on this. Also, in some slides, I discussed some peculiar patterns that have been observed in recent years concerning horizontal branch stars, mainly the presence of a peculiar rotational pattern and also the presence of strong chemical peculiarities in blue horizontal branch stars. I don't want to bother you with the numbers and so on. In this table, you can see how the helium core mass at the helium ignition for low mass stars is affected by the change in the physics that you can use for computing stellar model. We simply applied a change in the physical inputs, depending, the change was related with the estimated uncertainty on that physical inputs, and we verified what was the impact on the helium core mass. Just to summarize, not losing time discussing numbers, if this is the uncertainty cake for the helium core mass at the helium ignition for low mass star, the larger portion of the uncertainty is related to the, our poor knowledge of the conductive opacity, the uncertainty in percentage of the order of 40%. And let me remember that conductive opacity is a fundamental ingredient in order to evaluate what is the efficiency of heat transport in stellar matter when you are in condition of partial and strong electron degeneracy. Another important piece of uncertainty is coming from the efficiency of atomic diffusion, about 40%, and minor contributions are provided by the radiative opacity, the efficiency of the triple alpha reaction rate, and plasma neutrino cooling, let me say. When you combine all together the uncertainty associated to the different physical inputs that we need to use for cooking stellar model, we can obtain a maximum change in the helium core mass of the order of 0.01 solar mass. That could appear as a small amount, but it is really a huge amount, because a change of this order of magnitude in the size of the helium core mass translate in a change of 0.1 magnitude in the brightness of the tip of the giant branch and of the luminosity of the zero-age horizontal branch. And so I show now what is the current situation concerning stellar model concerning the prediction about the helium core mass and luminosity at the helium ignition. And in this plot, you see, as a function of the metallicity, the helium core mass at the helium ignition at the tip of the giant branch from different authors. And you can see that when you forget about the Padua model that shows a very erratic and strange behavior, I have no time to enter, time to discuss this behavior, you see that the uncertainty at fixed, or let me say the spread at fixed metallicity among the different models is of the order of 0.003 solar mass. It is quite smaller in comparison the amount, the quantity that I suggested you, provided you. And the fraction of this difference is related to difference in the adopted helium abundance, physical inputs, and so on. So the agreement seems to be very good when excluding the Padua model. And this is the situation concerning the bolometric brightness of the tip of a giant branch from the different authors. And here you see, when once again excluding the Padua model, the black lines and the solid and dashed line, that you have a spread of the order of 0.15 magnitude. That is, in some sense, quite large, let me say. So, can we constrain the accuracy of our model, and so the accuracy of the physics that we are using for computing this kind of model? The answer is yes, and we can use the brightness of the tip of the red giant branch observed in star cluster in order to constrain this. In this plot, you see the high Cousin band magnitude, the absolute high Cousin band magnitude of the tip of the giant branch as a function of the metallicity, and the 2 points with the error bar correspond to the measurements of this feature in the globular cluster Omega Centauri 47 Tucana. Okay? The red line corresponds to our calibration that we obtained more or less 10 years ago. And the blue line, is the calibration that we obtain when we improve the treatment of the conductive opacity. In particular, more or less 5 years ago, we published the new conductive opacity in collaboration with Potekin, and the situation, as you can see, improved a lot. Now, within 0.5 sigma, we are in agreement with the observation. So the situation is really improving a lot. And here is the situation concerning horizontal branch. This is the luminosity of the zero-age horizontal branch, once again as a function of the metallicity from different authors. And you can see that the difference are of the order of 0.15 magnitude when you account for the more recent prediction, and all model but the Dortmund one, the dotted one, the green line, predict the same dependence on the metallicity. The red line corresponds to our prediction before the improvement in the conductive opacity. When we include the new conductive opacity, the situation is here, the magenta line, and you can see that the agreement with the same empirical estimate of the brightness of the zero-edge horizontal branch in globular cluster, the cross here, is now improving significantly. So what we can say is that we have still some significant uncertainty in the computation of horizontal branch stellar model, but in the last 5 years we have obtained a big improvement in the accuracy of this model. Now, let me come back to the horizontal branch morphology. This is once again a color magnitude diagram for a galactic globular cluster, the horizontal branch with overimposed the theoretical zero-edge horizontal branch, with also listed the effective temperature of the different model. And you can see that when moving from the red portion of the horizontal branch toward the blue portion, the blue direction, you have an increase in the effective temperature. When you analyze in detail this behavior, you compare with model, and you can see that this distribution in color of horizontal branch stars can be really interpreted as a distribution in mass, but as first-order approximation, let me say. Now we know that the situation is changing. So in principle, this was, I already mentioned before, the distribution in color of horizontal branch star has been considered an evolutionary sequence of stars having the same helium core mass but different envelope mass, as a consequence of different efficiency of mass loss along the regime branch. These are evolutionary sequence, horizontal branch model, for different assumptions about the envelope mass. The envelope mass is decreasing when moving from the red side to the blue side of the horizontal branch. And for this reason, this approach has been used for estimating the efficiency of mass loss along the regime branch, the previous evolutionary stage. Now we know that this approach, as a consequence of the discovery of multiple stellar population, cannot be longer applied. This can be applied only for dwarf galaxy, just between brackets, because in that case we know that there is no evidence of multiple population. Okay? But this is another story. Now, let me discuss the horizontal branch morphology in the context of the second parameter problem. This problem is really a long-standing problem. It was discovered, if I remember, in 1955 by Sandage, that observed that the color magnitude diagram of different clusters with the same metallicity, and the situation is this one. You can find several pairs of globular clusters in our galaxy that have exactly the same metallicity, but completely different morphology concerning the horizontal branch. These are, for instance, the famous pair M3, M13. They have exactly the same metallicity, and you can see that in this case, you have a red horizontal branch. Here you have an extremely blue horizontal branch, and that you can see here. Let me say that the metallicity is the first parameter governing the morphology of the horizontal branch. We know this since our study of stellar astrophysics. Increasing the metallicity, redder became the average color of the horizontal branch. So, why we have clusters with the same exactly metallicity, high-resolution spectroscopy confirms this, but with so different horizontal branch morphology? This was, in its sense, the second parameter problem. What is the additional parameter that is driving the horizontal branch morphology? And let me say, until a few years ago, there were many suggestions, many possible candidates as a second parameter. Age, helium also was suggested, but with no convincing evidence, difference in CNO abundance, different pattern in rotation, different efficiency of mass loss. But any one of these candidates at the end missed a complete, let me say, confirmation of its responsibility. So, let me discuss now some additional peculiarity that we know since a long time and that until few years ago were not completely explained at all. The first one is this one. There are globular clusters that show a very peculiar horizontal branch distribution with the bimodality. Here you see the case of NGC 2808, a famous globular cluster. You have a red stubby horizontal branch and a very extended blue tail. Also, in some clusters, you see that along the horizontal branch distribution, this is once again the case of 2808 that we studied 14 years ago, and you see that we have some gap here, the region where you have no star, let me say, all the statistics is very few, and your star along the horizontal branch can reach a really very high effective temperature, something around 30,000 degrees. And it is very difficult in the canonical stellar evolutionary framework to produce this kind of star, because your star have to lose an incredible amount of the envelope. You have the star that should populate this region, if you account only for efficiency of mass loss, have extremely teeny envelope mass. It is very difficult to explain how this star can lose a huge amount of mass along the region branch stage and being still able to reach the horizontal branch. So why this star cannot move directly to the white dwarf cooling sequence, okay, without igniting helium burning. Another interesting peculiar evidence, was the discovery of blue horizontal branch morphology in very metal-rich globular cluster. This is a famous globular cluster embedded in the bulge. It's 6388, but there are also different cases. This is a very metal-rich globular cluster, more metal-rich than 47 Tucane. That is the typical prototype of metal-rich cluster. And you have a red stub horizontal branch, as expected on theoretical ground, but you have also a very extended blue tail. No chance to explain this in the canonical framework. And also, another peculiarity is the presence of a tilted horizontal branch. The tilted horizontal branch, also in this case, you see here how you can appreciate how the slope is, this portion of the horizontal branch is brighter than this one, was discovered thanks to the first data coming with the Wi-Fi camera 2 on board of the HT in 1997 by Rich and collaborators, and also there was no explanation for this. And the last peculiarity entering in the game was the discovery of blue star in many globular clusters. This is the case once again of 2808, and blue star are this star, this is an ultraviolet color magnitude diagram. This is the zero-edge horizontal branch, the blue line, and the red line is at the end of the horizontal branch phase. All stars belonging to the horizontal branch of this cluster are between the two lines, but there is a bunch of stars here that are fainter and hotter. There is no canonical explanation for the origin of this star. We know now what the stars are, but they are very peculiar objects. So, how we can explain all this peculiarity in a general framework, as a whole? This was impossible until a few years ago. But a few years ago, a new player entered in the game, and was the discovery of multiple stellar population in galactic globular cluster. I have no time to discuss in detail the many evidence of multiple population, so I provide you just a summary. The most striking evidence of multiple population in globular cluster is the fact that the stars belonging to the same cluster have not exactly the same chemical composition. In particular, the most evident signature is the presence of sodium-oxygen anticorrelation. That is the fact that in all globular clusters, you have this trend: oxygen-rich sodium-poor star, and also sodium-rich and oxygen-poor star with some continuity in the pattern. Okay? In some cluster, also there is the magnesium-aluminium anticorrelation. That is here. You have the coexistence in the same cluster of magnesium-rich aluminium-poor and magnesium-poor aluminium-rich star. And also there are many other peculiarities, as the presence of carbon-nitrogen, nitrogen-oxygen anticorrelation. There is the possibility of CNO some enhancement. In many globular clusters, this is not the case. As you can see here, the different point with different color refer to different cluster, and the sum of C plus M plus O is constant, but there are also some striking peculiarity, as the case of M22. These are stars belonging to the same globular cluster with different S element abundance, and you can see that there is a difference of more or less 0.2 dex in the CNO sum. Okay? And this was just confirmed a few weeks ago. This is the case of NGC 1851, in which Young and collaborators found two different distribution of stars with two different CNO C plus O abundances. Okay? But for our purpose, the most evident and important properties of multiple population in globular cluster is the helium enhancement. The proof of helium enhancement was mainly collected from photometry. This is the famous bimodality in the main sequence splitting in the globular cluster Omega Centauri. There is a blue and red main sequence, and there is a difference in helium between the blue and red main sequence stars of the order of 0.4. That is a huge amount. And this is the triple main sequence observed in 2808. All these observational properties in the optical bands can be explained only, and I emphasize only, assuming the presence of multiple helium abundance in this star cluster. Okay? Let me emphasize that 2808 was one of the clusters that I mentioned before several times. Okay? And I'll come back on this cluster in the following. For sure, there are also some different proof of the presence of helium-enhanced stellar population in globular cluster, mainly based on iron abundance, effective temperature scale changes, but also there are some spectroscopical measurements of helium abundance in globular cluster that confirm this helium enhancement. I have no time to discuss if you have questions. However, all this evidence of helium enhancement stellar population refer to non-evolved star, main sequence star, core hydrogen-burning star. We are talking about horizontal branch star. Horizontal branch stars are cold helium-burning star. The question is, can we have some proof? For sure, it's evident that if in the main sequence we have helium-enhanced star, I expect that the evolved star, the helium-enhanced evolved star, reach the horizontal branch. It's something that is not, I'll say, surprising. But we can have a direct measurement of the presence of helium enhancement also along the horizontal branch, so to have a direct proof. This has been done. The damning evidence was collected a few years ago in a paper we did in collaboration with Fabiola Marino. That is, we observed star along the horizontal branch of M4, red and blue, okay, and we made spectroscopy. And you can see that the red point corresponding to red horizontal branch star area are oxygen rich, sodium poor, and the blue horizontal branch star area that are sodium rich and oxygen poor. And they follow very well the oxygen sodium anticorrelation pattern observed in giants in this cluster. Okay? But, and also this has been confirmed in many other clusters, 47 Tucana, M5, NGC28, as we will see, and so on. So there is a one-to-one correspondence between the presence of oxygen sodium anticorrelation and the distribution of star along the horizontal branch, in the sense that the hottest star appear to be the star belonging to the, let me introduce now, second generation, the one that we expect to be helium enhanced, okay? When the red horizontal branch star here belong to the first stellar generation that should have a canonical helium abundance. This is the correlation. Sodium-rich, oxygen-poor imply some level of helium enhancement, okay, on the basis of nucleosynthesis in star. Okay, so the question arises immediately: does helium play a crucial role in driving the horizontal branch morphology? If there is some evident difference in the helium abundance between red and blue horizontal branch star, can be eventually the helium the driver of the horizontal branch morphology? This is something that has to be explored. Let me come back on theoretical ground. From our stellar model, we know that the helium enhancement has a huge impact on the evolution of stars. These are zero-age horizontal branch zero-age horizontal branch model for the same metallicity but different assumption about the initial helium abundance. And you can see how increasing the helium abundance in the cooler portion of the zero-age horizontal branch, the brightness increase, whereas in the hotter portion it decreases. This is due to the dependence of the luminosity of the horizontal branch on both the helium abundance in the envelope and the helium core mass. Here, since when you increase the helium abundance, the helium core mass decreases, okay, but the dominant effect is the fact that the luminosity depends also strong on the helium abundance, so they start getting brighter. Here, since the hydrogen binding shell is almost switched off, the only parameter that is relevant is the helium core mass, so since the helium core mass decreases, the luminosity has to decrease. Okay? Also, we know from our computation that helium enhanced horizontal branch star perform a more extended blue loop in the Hertzsprung-Russell diagram. The red line corresponds to a model with the canonical helium abundance, and the blue line is the same model for the same mass and metallicity, but an enhanced helium abundance. And you can see that this model, during its evolution, reaches hotter effective temperature. Okay? So all these effects combined together tends to produce bluer horizontal branch morphology. You can see here these are synthetic horizontal branch model. The red point corresponds to canonical helium horizontal branch star, and the blue point corresponds to helium enhanced horizontal branch star. The different panel, we are assuming the same efficiency of mass loss for both the helium canonical and helium enhanced stellar model in the different panel. But moving from this panel to this and this and this, we are increasing the average efficiency of mass loss of the regional branch. Okay, I'm assuming the same efficiency for helium normal and helium enhanced star, but I am enhancing the average efficiency of mass loss in the different panel. And you can see that regardless of the mass loss efficiency during the regional branch, the helium enhanced star the helium-enhanced one, are always located in the bluer portion of the horizontal branch, okay? So it is evident, if you in a star cluster have helium-enhanced star, this helium-enhanced star will populate mainly the bluer portion of the horizontal branch, okay? So, can we use the spectroscopical evidence and the theoretical prediction for understanding now some peculiarity in the horizontal branch distribution? And let me discuss in some detail the case of NGC 2808, the very peculiar globular cluster. This is the core magnitude diagram, the peculiar horizontal branch that I already discussed, and this was the first photometric evidence of multiple population in this cluster, the fact that you have a tripole main sequence, already discussed. So, and the tripole main sequence and the peculiar horizontal branch morphology has been, I would say, interpreted in terms of the presence of multiple helium abundance stellar population in this cluster. In particular, when you produce a synthetic horizontal branch model for different assumptions about the helium abundance, you can really recover the observed horizontal branch morphology with the red stub horizontal branch, the extended blue, and the intermediate color sequence, assuming that you have a distinct stellar population. The red stub horizontal branch is related to the canonical helium abundance. The intermediate color sequence is associated to an average helium abundance of the order of 0.3 with some spread, when the bluer horizontal branch star, the bluer portion, is associated with the more helium enhanced stellar component. But this is a synthetic simulation. Can we have a direct confirmation of this? We have obtained this a few months ago. The paper was published 2 months ago, if I remember. This is the helium abundance measurement from high-resolution spectroscopy as a function of effective temperature in horizontal branch star. For sure, you cannot measure from spectroscopy helium along the horizontal branch in cool stars because you have no good signal. You don't see the lines associated with helium because the stars are too cool. You cannot measure helium in the extremely hot horizontal branch stars because there the effect of atomic diffusion, okay, is changing drastically the surface helium abundance. So what you measure is not related at all with the primordial helium abundance of the star, the initial one, okay? So you can measure this only in a very restricted window that is more or less here, around 11,000 degrees, okay, this one. And what we measure is that with some spread, mainly due to the errors, it exists in this cluster along the horizontal branch an helium-enhanced stellar component that is really associated with this one, okay? So this was a direct confirmation of this. Also, going a little bit more in detail, you can also correlate the distribution of stars along the tripole main sequence with the distribution of stars in the different portions of the horizontal branch, the red portion, the extremely blue, sorry, the intermediate color one and the extremely blue, and you find that there is some good correspondence between the relative population ratios in the different branches. Okay? So there is a good correspondence. And also, the fraction of stars along the regional branch that appear to have different oxygen abundance, the oxygen normal, oxygen poor, and superoxygen poor, are in good agreement with the distribution of stars in the different sequences of the color magnitude diagram. So, let me now produce a global scenario for this cluster at least, relating horizontal branch morphology, main sequence peculiarity, and chemical pattern, okay, in the context of the multiple population. This is the oxygen-sodium anticorrelation. The black points correspond to the oxygen-sodium anticorrelation in the cluster 2808, okay? You have this very extended, let me say that 2808 together with the other cluster M13 are the 2 clusters that show the more extreme oxygen-sodium anticorrelation, the more extended one. Okay, and these are the horizontal branch and the main sequence. Now, can we explain photometric features and spectroscopical evidence in the same scenario? The idea is the following. Now we say the most oxygen-rich sodium-poor star are the first generation formed in this star, with the canonical helium abundance, the primordial one. These stars that we observe there in the oxygen-sodium anticorrelation are responsible for the red horizontal branch star and also for the reddest main sequence star, the one that are populating this region. Okay? The intermediate star in the the extreme star in the oxygen-sodium anticorrelation here are really the second generation star, and they have an helium abundance of the order of 0.4. If you want to ask me why we think that they are the second one. And this star, the more helium enhanced, are really responsible for the extremely blue horizontal branch star and also for the bluest main sequence observed in this cluster. The star populating the intermediate region in the oxygen-sodium anticorrelation are the third generation formed in this cluster, with an average helium abundance of the order of 0.3, 0.32, and they are responsible for the intermediate portion of the horizontal branch and the intermediate main sequence in this plot. Okay? This is the interpretation that now we give of the photometric evidence and spectroscopic evidence. Now, another peculiarity that I mentioned before, the presence of tilted horizontal branch. You cannot explain this tilt there is no way in the canonical evolutionary scenario. But now we can explain this, assuming that in this cluster we have the presence of two stellar components, an helium poor, helium canonical, let me say, red point here, this is the horizontal branch, synthetic horizontal branch simulation, and in the same time, an helium enhanced stellar population with some spread in the helium abundance. And you can see how now naturally you obtain a morphology that is in very good agreement with the observed one. Okay? Let me say that in this cluster we have strong evidence of multiple population. There is also a splitting in the main sequence. So this scenario is really confirmed also by other evidence. So is now the second parameter solved? Maybe. Few months ago, it's been published a paper led by Antonino Milone, but in collaboration with many persons present here, Matteo, Sebastian, Antonio Barisio, myself, and we studied the second parameter from a different point of view, let me say, in the context of the multiple population. What we did was to introduce two additional parameters, L1, L2. For my purpose, is important L2. L2 is the distance in color between the red giant branch and the most bluest point along the horizontal branch. This is used as a proxy of the length of the extension of the horizontal branch. It's just a parameter that you can invent, okay? And what we found is that this parameter, L2, the different color coding in this plot correspond to clusters with different metallicity, but there is a very huge correlation, a very good correlation between the parameter L2, that is the extension of the horizontal branch, and the absolute integrated magnitude of the cluster, okay? That is a proxy of the globular cluster mass, okay? Sorry? The closest are metal-rich cluster. Extra flat. In fact, they have essentially red stub horizontal branch. Okay, so L2 is very small. Apart, there's a two cross that are 6388 and 6441 that are two metal-rich globular clusters with a very extended horizontal branch that I mentioned before. These are intermediate clusters. The green point are clusters with the metallicity around minus 1.3. And so there's this correlation between the horizontal branch extension and the mass of the globular cluster. But all these globular clusters have been also studied in the context of a multiple population. And we know now that many of them host stars with different level of helium enhancement. Okay? So we try to find a correlation, if any, between the helium dispersion between the different subpopulations in the same globular cluster and the extension of the horizontal branch, L2. And once again, okay, you find that there is a good correlation. There are few clusters in this plot because there are few clusters for which we have good measurement of the helium spread between the different subpopulations, okay, so far. And you see, once again, that there is a good correlation between the horizontal branch extension, L2, and the difference in helium between the first and second generation in the same cluster, okay? And this is not surprising for sure. We found that there is also a correlation between the presence of helium spread in the different subpopulation in the same globular cluster and the mass, the integrated magnitude, means the mass of the globular cluster. Now we know that the multiple population phenomenon is stronger in more massive globular cluster. Larger is the mass of the globular cluster, stronger are the peculiarities that are present. So that means stronger level of oxygen-sodium anticorrelation, stronger helium enhancement, okay? So maybe now we can explain or provide some hint we can provide a better description maybe of the second parameter problem. These are the famous pair of globular clusters that I showed you before. What we think now is that the horizontal branch morphology is mainly governed by some global parameter. As global parameter means parameter that are relevant for all globular clusters in the Milky Way. So they are the main parameter at work in all globular clusters. And for sure, they are the metallicity, that is the first parameter governing the horizontal branch morphology, and also the age, because we know that not all globular clusters have exactly the same age. This we know very well from the measurements of the age of globular clusters from the main sequence turn-off brightness. So age is different between some clusters, and it has to play a role because the horizontal branch is affected by age. So these parameters are global. They work for all globular clusters in the Milky Way. But there are also, let me say, some non-global parameters. Non-global means parameters that are at work in a given globular cluster, but can be not at work in another globular cluster. Here, for instance, you see, maybe there is a parameter that is at work in M13, but it is not at work in M3, and we think now that this is really the helium spread between the internal helium variation between the different subpopulations hosted by a given globular cluster. Okay? We have now, for sure, the striking proof of this, but every observational evidence seems to suggest that it is a good interpretation of what we are currently observing in the Milky Way. Now, let me move to a not completely, but a different issue. We know since some time, let me say 10 years, that there are a huge amount of peculiarities in the horizontal branch stars in the same cluster. The most interesting one was found a long time ago by Frank Grundal during his PhD thesis. He found that if you collect data in the stronger filter, that means narrow band filter, of horizontal branch star in globular cluster, there is a jump. It's quite evident here, for instance. The line corresponds to theoretical prediction, and you see that the cool horizontal branch star in this color magnitude diagram are in the right position with respect to theoretical expectation. But also there is a jump. The star became brighter with respect to the theoretical model, and after they reach again the theoretical expectation. You can see also this in UMB filter in the case of 2808. The jump is this. This is the Grundal's jump. Okay? Another evidence that was collected a few months after the work of Frank Grundal was this one. It was once again a PhD thesis of Baer. It was an amazing work at the time. And he discovered there was some evidence of this, also collected 50 years ago, but at the time only 3-4 stars were studied. Now we have hundreds of stars for the same globular cluster. So what he found is that there is a clear presence of discontinuity in the abundance ratio when you consider the star along the horizontal branch at different effective temperature. In this plot, the different panels correspond to different elements: helium, iron, magnesium, titanium, silicon, and whatever. The red line corresponds to the abundance that you expect accounting for the original metallicity of the cluster. Okay, so since this is a metal intermediate cluster with a metallicity minus 1.5, I should expect that all horizontal branch stars show this metallicity, minus 1.5. But what he obtained was that stars hotter than 11,000 to 12,000 degrees show a strong level of iron enhancement. They are hugely iron enhanced. Also, titanium is affected, and phosphorus, chromium, other elements like magnesium and silicon. Magnesium is not affected at all. Silicon is affected with a less extent. On the other hand, helium is depleted in hot horizontal branch stars. This is a consequence of atomic diffusion being at work, the fact that I mentioned you before. Okay, so there is a settling of helium in the outer layer of this hot horizontal branch star. So, I forgot before. The Grundal jump starts exactly at 11,000 degrees. This effective temperature value became famous in the last 10 years. At 11,000 degrees, there is the starting of Grundal jump, and there is also the starting of the chemical peculiarities that I discussed. And all these evidence are circumstantial proof of the fact that atomic diffusion and radiative levitation are really at work in the horizontal branch star. This was something that was completely neglected until 10 years ago. The situation now, from theoretical point of view, is really not good, let me say, and I show now what is going. We know very well why 11,000 degrees is the crucial effective temperature, and you can see here this. This is a plot that shows you the location of the convective zone in the outer envelope of an horizontal branch star as a function of its effective temperature location along the ZAB. So going from here to here, we are considering star, red horizontal branch star, blue horizontal branch star. And in cool horizontal branch star, you have an extended convective envelope. This is the reason for which you have no diffusion has no impact, levitation has no impact, because mixing erases the effect of diffusion and levitation. But when you go go to hotter effective temperature, the convection zone disappears. There is the hydrogen 1, helium 1, and helium 2 convective zone. But at 11,000 degrees, that is more or less here, disappear both the convection zones associated with hydrogen 1 and helium 1. So the outer layers are stable against convection. So radiative levitation and diffusion can start to work. There is nothing erasing the effect of diffusion and levitation. So this is the reason for which we now understand why at 11,000 degrees we have this, all these peculiarities appear. Okay? And also, following the trend of the convective zone, we can explain why at the very extreme, portion of the horizontal branch, the radiative levitation should disappear because the helium-2 convection zone approach the surface. But the situation is not so good. We are trying to reproduce this, and the situation is not good. I'm showing you the result provided by the Canadian group, Michaud and collaborators. In this plot, you see what is the expected iron enhancement for a star with given metallicity as a function of their effective temperature. So the lines here are really evolutionary sequence, okay? And the color portion of each sequence correspond to, if I remember, the time in between 15 and 30 million years after the zero-age horizontal branch. Okay, what this plot is saying? It's saying that if you increase the effective temperature of your model, the enhancement is larger. So radiative levitation is more efficient. Good, this is what we observe. But it is in agreement with the observation, and the situation is this one. These are data for the cluster M15. In the hotter portion of the horizontal branch, the model predicts the correct level of enhancement. Okay, although there are a lot of free parameters in this model. Okay, we have some turbulence accounted for and blah blah. Okay, but here they work well. The same model with the same free parameter tuned in the same way are not able to reproduce this. Observations say that stars cooler than 10,000 degrees do not show evidence of enhancement in the iron abundance, but the model predicts a significant enhancement. So there is something wrong in the model, something that has to be corrected. Okay? Another very important peculiarity that was found in globular cluster, more or less in the same year, 14 years ago, was the fact that horizontal branch stars rotated. This was really surprising because we know that all stars rotate during the main sequence with different efficiency and so on. But when low mass stars climb up the giant branch due to the strong increase in the radius of the star and the huge efficiency in the mass loss, a huge amount of angular momentum should be lost. So in our idea, when I was a student, the general idea was that horizontal branch stars, they do not rotate. Okay, they are very stable stars. We are happy about this. Okay, this was not the case. When you analyze in detail the rotational pattern of horizontal branch stars in globular cluster, what it was found once again by Baer was that cool horizontal branch stars rotate, and rotate with average VC9 velocity of the order of 20 km per second. That is a huge amount, okay? When the hot horizontal branch stars, they do not rotate. The average velocity is around 4 km per second, compatible with no velocity at all, okay? When you account for the error. And the same pattern is also obtained in the field, okay? Cool horizontal branch stars rotate very fast, and hot stars do not rotate, with some exception. So this evidence were, let me say, embarrassing, because we found that they rotate, and they should not rotate. Some of them rotate fast, something that we cannot understand, and also we do not understand at all the fact that there is a discontinuity in the rotational pattern as a function of effective temperature. Let me say that so far we have no theoretical interpretation of this. Okay? But it's interesting to know that there is a huge link between the chemical peculiarity and the rotational pattern. Okay? This is, for some clusters collected all together, the level of the abundance of iron at the surface as a function of the effective temperature. Okay? You see here that all stars hotter than 11,000 degrees, the position of the Grundle jump, are hugely iron enhanced. This is the effect of radiative levitation being at work. Cool stars are not enhanced. Radiative levitation is not at work. Here is the pattern of the VC9 rotational velocity as a function of the effective temperature for the same star. Okay? And you can see that all stars that show strong evidence of radiative levitation are not rotating. The stars that do not show anomaly are significantly rotating, with one exception. This star is quite hot, but it does not show any any level of enhancement, and it is rotating very fast. Okay? So maybe there is a strong link between rotation and levitation. Okay? But, okay, this is what I already said. So, can we explain this? In principle, no. There is no model able to explain altogether the rotational pattern and levitation, but there is an interesting scenario that I suggest just for completeness, that is once mentioned, suggested by Quivi and collaborators after they disappeared from astrophysics. I don't know why. This is the pattern of rotational velocity as a function of the effective temperature. The red dot corresponds to the empirical measurement, in the sense that cool horizontal branch star rotate with the average velocity around 20 km per second, and hotter star practically do not rotate. The different line correspond to, okay, they assume that the stars are rotating without taking care of why they rotate, okay? And what they study is the impact of meridional circulation. When you have rotation, you have some induced mixing. This mixing can mix all the outer layer, so erasing the effect of levitation and diffusion, okay? So they say, what they note is that they observe the rotational pattern of star current in horizontal branch is compatible, all cool stars rotate faster than the minimum velocity that you need in order that rotational velocity induced mixing erase the effect of levitation. Also, hot stars rotate at lower velocity, have a velocity that is lower than the minimum velocity that you need to have efficient meridional circulation, and so this star can really show strong chemical anomalies. Okay, so they say rotation and relative levitation are in some sense linked. If the star rotate fast enough, they can completely erase the effect of levitation. This is the reason for which we observe stars that are rotating fast, are hot enough, they are rotating fast, but they do not show any evidence of relative levitation. But it was some kind of, I would say, interpretative scenario, but there is no clue at all on why horizontal branch stars rotate. And I would like just to conclude with another problem that we have, if I have time for this slide, concerning rotation. Let me say, we have no idea how we can introduce rotation in our model, okay? The main problem are related to the fact that we don't know how to treat the redistribution of angular momentum when the star moves from the main sequence to the regional branch. We don't know, for instance, if in the giants, in the convective zone, we need to assume solid body rotation or conservation of specific angular momentum. We have no idea at all about this. And so, the few attempts that has been done to interpret the evidence have been obtained more or less more than 10 years ago, as you can see. These are the same empirical data, rotational velocity as a function of effective temperature for some globular cluster, and you can see the line corresponds to different rotational model, rotational stellar model, for different assumptions about the conservation of angular momentum, and you can see that if you want to reproduce the low velocity of hot horizontal branch star, you are not able to reproduce the high velocity of cool star. If you want to reproduce the pattern, rotational pattern of cool horizontal branch star, you miss completely the location of star of hot horizontal branch star. So there is really a huge problem on that. I wish to conclude with just one topic that we studied a few months ago in collaboration with Dr. Matteo Monelli, that is the apparent anomaly in the distribution of second-generation star along the asymptotic giant branch, the progeny of horizontal branch star, in a globular cluster. We know that when we observe globular cluster with spectroscopy, we found that the number of AGB stars showing chemical peculiarity, possibly related with the multiple population phenomenon, decreases significantly in comparison with stars with the same peculiarity along the red giant branch. Okay? In particular, it was also found that globular clusters that have a very blue horizontal branch morphology, this is the minimum mass along the horizontal branch, so this is a proxy of the blue horizontal branch extension. In this side of the plot, there are globular clusters with the very blue horizontal branch. This ratio, the number of AGB stars with respect to the number of red giant branch stars, decrease significantly. Okay? And in particular, in the case of NGC 6752, was claimed by Campbell and collaborated in 2013. There was a paper appeared on Nature, okay, that in this cluster there is an anomaly. Along the AGB of this star, there is no second generation star. They measure the sodium abundance, let me note, only sodium, okay, in the IGB star. They do not measure iron. I'll come back on this. And they study the distribution of sodium over iron as a function of the temperature, effective temperature. The open dot are region branch star, and the red point are region branch star measured by Campbell, and blue point are measurement made by Campbell of AGB star. And they say, oh, all AGB star are below this line that they suggest is the separation between second generation star and first generation star. So they claim, okay, all the AGB stars in this cluster are first generation star. There is no possibility to observe second generation AGB star. Okay. They made some simulation, and they published this in their paper. They say, in a canonical evolutionary framework, horizontal branch star, helium-enhanced star belonging to this cluster should reach the AGB stage, so they should be present. Since we do not observe this star along the AGB, what we suggest that there is a strong efficiency mass loss along the horizontal branch that is really removing, it is really, this efficient mass loss does not allow the star to reach the AGB. So they miss completely this stage, behaving as AGB manqué star, okay? Okay, this was published. But we studied more in detail this, we computed several stellar model computation, and what we found is that the minimum mass loss along the horizontal branch that you require in order to force a star to not reach the AGB stage when helium at the center is exhausted is 10 up to minus 9 solar mass per year. That is a very huge mass loss efficiency that is at odds with the mass loss prediction, is at odds with the efficiency of radiative levitation in horizontal branch star, because mass loss erases the effect of radiative levitation, and it is also in contrast, in sharp contrast with the presence of radial pulsation in SDB star. So there is a problem. We analyzed more in detail this, and what we did was to perform some synthetic horizontal branch simulation. We know from high accuracy photometry and spectroscopy that in NGC 6752 there are 3 distinct subpopulations with different level of helium enhancement. So what we did was to try to simulate the observed horizontal branch with our model for different helium abundance, and to see if some of this star, the progeny of this star, of this second generation star, reach the AGB. Okay? You can note that our simulation is in very, very good agreement with the observation. The parameter R2, that is the number of AGB star over horizontal branch star, is perfectly reproduced within the error. And, okay, I don't enter this into detail. What we found, okay, was that our simulation predicted that along the AGB stage of this globular cluster, 50% of stars are really first generation stars, but the 50% belong to the second generation. So according to our simulation, if we want to reproduce the horizontal branch morphology and the distribution of helium abundance in this cluster, our model predicted that second generation stars have to be present along the AGB. So there is a sharp contradiction between our simulation and the spectroscopic measurement of Campbell. There is no way to find a way to conciliate this, to find agreement between this expectation. But maybe there is a way out. The way out is the following. I don't discuss this. I mentioned that Campbell measured only sodium, not iron. And after he studying the distribution of sodium over iron, and according to the abundance of sodium over iron, he's saying what are first generation and second generation stars. Okay? This is the case of M13. M13 is another peculiar globular cluster with oxygen-sodium anticorrelation. In this cluster, Johnson and Pilashowski, 2 years ago, the oxygen-sodium anticorrelation found that there are, the red point, AGB star belonging to the second generation. So the reason is, the question is, why second generation AGB star are present in M13 and should not be present in 6752? There is, but in this case, Johnson and Pilashowski measured not only sodium, but also iron along the AGB. So they are fully consistent measurement. Now, I am not a spectroscopist, but I know something about stellar evolution. So, this is a plot taken from Michaud and collaborator. This is the level of concentration variation in a horizontal branch star for different elements. The different color coding say you how much this element is enhanced in the different layer as a consequence of radiative levitation. Okay? And if you look to sodium and iron, stellar model predict that sodium and iron along the horizontal branch are strongly enhanced. So, let me assume, it's a qualitative scenario, that along the horizontal branch we have some low efficiency mass loss, that is possible. 10 to minus 12, 10 to minus 14. This mass loss is really removing sodium and iron from your horizontal branch star, okay? As a consequence of mass loss, because the enhancement is strongly concentrated in the outer layer as a consequence of levitation, okay? After this star moves from the horizontal branch to the AGB, where you have mixing, extended mixing process, okay? If you measure sodium only, okay, but you don't measure iron, and you use the same iron abundance of red giant branch star that were not affected by relative levitation, you are overestimating the abundance of iron in your AGB star. So you are modifying your estimated sodium of iron abundance with respect to the actual one, okay? And this can introduce a bias in your model, okay, in your measurements. We think that maybe this is the solution of this conundrum between stellar model and Campbell measurements, and so spectroscopical measurements, self-consistent spectroscopical measurement of both sodium and iron in the AGB star of 6752 should be really done. I conclude. I think that you have understood that the horizontal branch is really a very good amplifier. Everything occurring in the early evolutionary stage is amplified along the horizontal branch. And so now we know that if you want to understand how horizontal branch start, we will be able to build up this amplifier, accounting for chemistry, rotation, levitation, turbulence, diffusion. But it's something that is very risky, and we have not found any way to solve this so far. And just for fun, I would say that maybe now we are entering a new era of studying horizontal branch star, thanks to the variability of astroseismology. This is the data collected by the Kepler telescope. For all these giant and horizontal branch star here, we have now a very good measurement of the pulsational, non-radial pulsational spectrum, and so maybe using a different amplifier, that is the sound of star, we can now enter inside the star and try to understand how they are made, what are the size of convective core, what is the efficiency of different mixing. And just for your fun, these are color magnitude diagram for star cluster of different age. The age is decreasing when moving from top panel to bottom panel, and now we can really listen the sound of star. This is not a real sound. It has been amplified by a factor of 1 million in order that you can see. This is the sound of 1.1 solar mass horizontal branch star, the sound of 1.6, and sound 2.5. So maybe listening the sound of star, we can really enter inside the star and to understand how they really work. Thanks for the... I think so. I listen. A mass. Sorry, I went on to the talking about the correlation between helium abundance and... Ah, yeah, okay, sure. Yeah, let me, I have not the slide. Okay, the situation is this. We can understand, for sure I have no time to enter into detail, discuss in detail the multiple population, how they form and whatever. The idea that we have now is that in a globular cluster forms the first generation, okay? And after form the second generation. The second generation is formed from matter that has been processed by star belonging to the first generation, okay? There are some suggestions about the possible polluters, massive star, fast rotating massive star, or AGB star, okay? Whatever. In any case, if you want this kind of oxygen-sodium anticorrelation, so this change in the light element chemical pattern, you need to assume that high temperature proton capture, high temperature hydrogen bonding is occurring, okay? So you can interpret this light anticorrelation as a consequence of hydrogen bonding, high temperature, okay, burning. And if you have hydrogen bonding, you have helium production. This is something for which we can be absolutely sure. More extended is the light element anticorrelation. So more strong has been the nuclear processing of this matter, the hydrogen burning, larger larger has to be the helium abundance that we expect to observe. Okay, this is the. Okay, no. Okay, no. High temperature photon capture by itself is occurring in AGB star during the thermal pulsing stage, rotating massive star in general, okay, and also during supernova. But you have many spectroscopical constraints. We do not observe only for many clusters. Let me exclude the case of Omega Centauri, Tarzan, whatever. Let me consider once again the case of 2808. It's a normal globular cluster, no metallicity spread. For the majority, for the bulk of the galactic globular cluster, we do not observe any metallicity spread. So this seems to suggest that the massive stars, okay, the one that after explode as type 2 supernovae, cannot be responsible for this, because otherwise we should observe a significant level of metal enhancement in the different subpopulations that we do not observe, apart the case of Omega Centauri and other few cases. Okay? So the spectroscopic evidence that we can collect actually poses several strong constraints on who are the polluters. Okay? For instance, AGB star during the thermal pulse stage, are able to perform high temperature photon capture. But you need to exclude the less massive AGB star. Why? Because less massive AGB star perform the tilted edge up, and this would enhance significantly the carbon abundance at the surface, and so the matter that is ejected by this star would be strongly CNO enhanced. And we do not observe this in many globular clusters, once again. So maybe the polluters are AGB stars. I know that he doesn't like AGB star, but now you like, perfect. But maybe are the ones that are more massive than 4 or 5 solar mass, the ones that are experiencing the hot bottom burning, but not the tilted edge up efficient. Yeah, it's true. Yeah. Yeah, it's true. It's completely true in the sense that I was, nascondendo la carta, playing, when I answer you, in the sense that the anti-correlation are produced by high temperature photon capture, okay? But the observed anti-correlation, the dilution that you observe in the sodium-oxygen anti-correlation, cannot be produced only by stellar nucleosynthesis. You need to mix the heats produced by stars with some kind of pristine gas that has not been processed by nuclear turning in order to really obtain that pattern. It's something very complicated. I have to say that we have collected so far a huge amount of photometric, spectroscopic evidence for multiple populations. We are able to explain many features of the horizontal branch of, but we don't know so far how really the second generation stars form in a globular cluster. So do you mean, sorry, the question is how massive has to be the first generation in order to produce, no. How much has to be the amount of reservoir? More or less it has to be 50%, is in equal proportion with the yields produced by the star. 50-50, let me say. Exactly. Yeah. With a strong difference from one cluster to another cluster, but roughly speaking, 1-to-1.
Okay. We're a bit out of time, so I invite all of you to keep talking to Santi downstairs at the Café Científico, and let's thank the speaker again. Thank you.